In the last lecture, we started discussing transport characteristics of particles, and we looked at particle dynamics, particularly the diffusional characteristics of particles as well as their transport under an electrical field. And later in the lecture, we began our discussion of drag force that is experienced by particles that are suspended in a fluid and the gravitational or body forces that act counter to the drag force, particularly under settling conditions for particles. Now, just to recall, the drag force of a particle in a flow Fd depends on the Reynolds number. When Reynolds number is much smaller than 1, that is under creep flow conditions, we said that F drag equals 3 pi mu dp v over cc, where mu is the dynamic viscosity of the fluid, dp is the particle diameter, v is the relative velocity between the particle and the fluid, and cc is the Stokes-Cunningham correction factor, which is approximately proportional to the inverse of particle diameter for very small particle diameters. When Re exceeds 1, then the drag force is expressed in terms of drag coefficient times pi dp squared by 4 times half rho gas v squared. Of course, the definition of Reynolds number is dp v rho over mu. The Reynolds number versus the drag coefficient relationship again can be expressed as CD versus RE, where initially there is a steep drop with respect to the Reynolds number with a slope that is expressed as 24 over RE, and then for Reynolds numbers exceeding 0.1, essentially the drag coefficient reaches an asymptotic value. Now, we also saw that the body force can be represented as pi dp cubed over 6 times rho p minus rho f times an acceleration g. Here, of course, the rho p minus rho f refers to the differential in densities between the particle phase and the fluid phase. Now, in the case where you have sedimentation occurring, where you have particles that are suspended in a fluid, the gravitational force Fg is acting in this direction and the drag force is essentially opposing it, and because of that the particle reaches what is known as a settling velocity or a terminal velocity, and the expression for that can be obtained essentially by equating Fd to Fg. So, when you do that, now let us take the case of very small Reynolds numbers. Under settling conditions, mostly the Reynolds numbers are very small. So, you can assume that the drag force will correspond to that. So, it is 3 pi mu dp times, in this case of course the velocity will now be the terminal velocity Vt over cc, and this is equated to pi dp cubed by 6 times rho p minus rho f times g. So, pi cancels out, dp cancels. So, it's Vt equals, in the denominator you will have 18 mu, and in the numerator you have dp squared times rho p minus rho f times cc times g, right. Now, this term is referred to as tau, where tau is the so called particle relaxation time. So, you can express the terminal velocity as the acceleration associated with the body force times the characteristic particle relaxation time. So, in other words, Vt this can be simply written as tau times g. Now, if you look at this expression, the dependence of the terminal velocity on particle diameter is it goes as dp squared for large particles. However, for finer particles, as we have seen earlier, Cc itself goes as 1 over dp. So, for finer particles that are in the micron and less size range, the actual dependence of the terminal velocity on particle size is linear, it is not quadratic. So, Vt is proportional to dp squared for dp values typically in excess of a micron, and it goes roughly as dp for particles that are less than 1 micron. Now, that is an important consideration, and in fact, for nanoparticles, as you start approaching the nano regime, the settling velocity dependence on particle size is, what do you think? I mean, is it going to be linear, quadratic, or less than linear? Actually, if you just extrapolate this, as particles become finer and finer, the dependence on particle size will keep decreasing. So, for nano sized particles, in principle, the settling velocity is independent of particle size. It is just like molecules, right? Do molecules settle? Does the settling time for molecules depend on their size? No, because they are just kind of randomly moving around. So, there is no size dependence per se, right? And that is exactly what happens. Another thing you should do as an exercise is assuming that the particles are actually moving at this with this drag force. In other words, the Reynolds number is high enough that this expression applies. Then what happens? If you equate that to the gravitational force, what kind of expression do you get for terminal velocity? So, I suggest you work it out, and you will see that the dependence on particle size is reduced further when you take that expression into account, again indicating that very fine particles have higher velocities, and because of that their motion can be considered to be similar to high Reynolds number motion. And that is another reason why, if you actually calculate the particle size dependence of the terminal velocity for very fine particles, you will see that there is virtually no size dependence. So, work out that exercise. You should also look at the case where this g does not have to be just gravitational. Supposing this whole thing is in a gravitational or in a centrifugal field, so that you are applying a separate body force through your centrifugal motion, then this g effective will be equal to g plus the rotational term, which is some sigma squared times x, where sigma is the rotational speed and x is the distance of separation between the axis of rotation and the centroid of the particle, right. So, again in this case, if you want to find out the settling velocity under centrifugal conditions, where the centrifugal field is acting in concert with the gravitational field, you have to substitute for the effective acceleration term, a term that includes gravitational pull plus the pull due to the centrifugal field that you have superimposed on top of the gravitational field. So, the net effect of that is going to be that Vt in general equals tau times g effective, where g effective includes the gravitational field plus any other body force field that you have superimposed on that field. Okay, now let us look at how this leads us into our definition of a dimensionless parameter that governs inertial transport of particles. Now, as I mentioned in the last lecture, as particle size changes, so does the predominant force field. So, when particles are very, very fine, diffusion and electrostatic effects dominate. As particle size increases to an intermediate region, drag begins to make its presence felt. As particle size increases beyond that to supermicron values, then inertial effects begin to dominate. So what do we mean by inertia? Inertia is what we call the behavior of a particle where it starts to deviate significantly from its carrier fluid. So for example, if you have a solid surface and the fluid is approaching this solid surface, let's say in a normal direction, then you would expect the fluid streamlines to look something like this, right, with possibly recirculation or stagnation in between. So if you have very, very fine particles, let's start with molecules. What would molecules do? They would basically follow the streamlines, right? They will just keep going along with the fluid streamlines. Let's say the particle size gets bigger, gets to the nano sizes. What are they going to do? For the most part, they're going to do the same thing. They're going to keep following fluid streamlines. But as you keep increasing particle size, fine particles may follow the streamlines. But what if you have a particle that is this size? Is that also going to want to follow the streamline? No. It's going to want to separate itself from the fluid streamline and follow a different trajectory, and that is because of the inertia that it has. So the measure of inertia is really the tendency of the particle to behave in a fashion that is completely different from the carrier fluid in terms of its transport characteristics. And inertial effects will obviously depend on the size of the particle. As the particle gets larger, it will have a greater tendency to separate itself from fluid streamlines. Now when that happens, you have to essentially start considering the particle as a separate phase. You really cannot assume that it's behaving like a heavy molecule, right? So there is a limit of size once it crosses which the effects are definitely inertially dominated. How do you find out what that size is? What is that critical size at which inertia becomes extremely significant? The dimensionless parameter that dictates the relevance of inertia is called the Stokes number. So what is the definition of Stokes number? Well, you start with the definition of what is a characteristic relaxation time for the particle. Now let's assume that this particle here starts with an initial velocity of v0. What is its stopping distance? In other words, how far will it go before it comes to a stop? Now that's something you can basically obtain by taking the velocity equation and integrating it. When you do that, you find out that the stopping distance s is simply relatable to the particle relaxation time tau multiplied by v0, the initial velocity of the particle. So the greater the particle relaxation time and the greater the initial velocity of the particle, the greater will be its stopping distance. Now what do you relate this to? Your surface will have some characteristic dimension, let's call that some d. Depending on the physical nature of the problem, the relevant dimension may be longitudinal or transverse to the flow, but there will always be a characteristic length which is associated with the target substrate. The definition of Stokes number is simply S over d. It is the ratio of the stopping distance of the particle to a characteristic dimension of the surface which is causing the particle to come to a stop. Now in terms of the Stokes number then, what is the physical meaning of the Stokes number? When the Stokes number is much smaller than 1, it implies that inertial effects are virtually absent. when Stokes number exceeds 0.1, inertial effects become significant. So, for any physical problem, you calculate the Stokes number associated with particle motion and find out its magnitude, and that will pretty much give you an idea of how important inertial effects are. Now, one of the key things to remember here is the Stokes number is not only related to the stopping distance of the particle, it also refers to the dimension of the surface. In other words, you may have a particle that has a relatively small stopping distance. However, if the characteristic surface dimension is also much smaller, then your Stokes number can still be high. So, it does not depend on the absolute magnitude of your terminal velocity or your stopping distance. It is a relative measure of how much distance it will take to bring the particle to a stop to a physical dimension of the surface that it is encountering. Now, why is Stokes number important from a particle transport viewpoint? Well, the reason is, of course, when we say inertial effects become dominant, what we are saying is that you really cannot treat the particle as a component of the flow anymore. You have to start following the particles separately. So, in terms of our analysis of the flow problem, I am sure you have heard about Eulerian and Lagrangian treatments of flow. So, the Stokes number much smaller than 1 lends itself to the Eulerian approach, where you do not consider the particle phase separately. However, once the Stokes number exceeds 0.1, you have to use the Lagrangian analysis, where individual particle trajectories have to be tracked in order to describe the dynamics of particle transport in the problem. So, from a flow analysis viewpoint, from a fluid dynamic modeling viewpoint, from a CFD viewpoint, the Stokes number makes a huge difference. And in terms of particles collecting on a surface, again, Stokes number has a huge influence. There is a parameter called collection efficiency. So, if you have a surface and you have a flow on top of it, which can be either parallel to the surface or perpendicular to the surface, let us say that this flow is characterized by some velocity u far away from the surface. Let us say the fluid has some density rho, and let us say that the particle mass fraction far away from the surface is some omega p infinity, where p stands for the particle phase and infinity stands for far away from the surface. Then you can actually estimate a flux of material across this surface. So, flux of material or flux of particles flowing over the surface will be simply equal to rho times u times omega p infinity, right. Rho u stands for the total flux of the fluid over the surface, and when you multiply it by the mass fraction of particles, that gives you the flux of particles across the surface. Now, let us say that some A projected is the projected area of the surface that is encountering the flow. Then the rate of collection of particles on the surface, which we can write as mp dot, where m stands for mass, p stands for particles, and dot stands for unit time. So, this is mass of particles collected on the surface per unit time will be simply equal to rho times u times omega p infinity times the projected area, right. So, this is the total, sorry, this is not the mass collected per unit time, this is mass flowing across the surface This is the mass of material flowing across the surface per unit time. The parameter capture efficiency reflects what fraction of that material actually collects on the surface. So let us say that this is the amount of material that is flowing past the surface per unit time. Let us say that there is some collection rate MP dot, which is let's call that MP dot collection, which is the rate at which particles are collected on the surface. Now, why is this different from what we have defined earlier? Now, come back and look at this. When you have a surface which is encountering a flow containing particles, a lot of particles will be flowing across the surface, but not all of them will actually collect on the surface. Many of them will strike the surface and rebound. Many of them may never encounter the surface, right? So the actual collected material will be smaller than the material that is available for collection. So this parameter eta capture efficiency is basically the ratio of the two. So it is the collected material MP dot collected over MP dot flowing. It's a ratio of the rate at which particles are collected on the surface to the rate at which they are flowing across the surface. Now, in many process industries, this capture efficiency is a very, very crucial parameter. In some cases, for example, in power plants, the rate of fouling of heat exchanger surfaces very much depends on this collection efficiency or capture efficiency. Ash particles from combustion gases can deposit on heat exchanger surfaces and cause a deterioration of heat transfer. So in power plants that are burning dirty fuels like coal, particle collection on the heat exchanger surfaces and the associated development of a fouling layer are of great concern. So in those industries, you want to minimize this parameter. You want to keep this capture efficiency as low as possible. And same thing in microelectronic industries, where you have critical circuits and other components that are potentially being exposed to contamination. And there again, what you want to do is minimize your capture efficiency. As long as the particles are not actually collecting on the surface, you don't care. If they're just flowing past, that's okay. It's the particles that actually collect on your critical surfaces that can cause reliability and other problems. So typically this capture efficiency is a crucial parameter that must be minimized in many process applications. But if you're designing a filtration system, you want to maximize it because you want your filter to collect as large a fraction of particles as possible, right? So it's not that you always want to minimize it, but you always want to calculate it. The capture efficiency is a very crucial parameter in any system involving particle suspensions coming in contact with solid surfaces. So how is this related to the Stokes number? That is really the key question to answer. Is there a relationship between Stokes number and the capture efficiency? If so, what is its qualitative nature and what are the implications of this? So if you plot capture efficiency versus Stokes number, what kind of a behavior do you expect? Let's say that this starts from 0 and goes up to 1, and here you start from, let's say, 0.001, 0.01, 0.1, 1. What kind of a shape do you expect? It's actually an S-shaped curve. So you'll see a behavior that looks like that. When you have very low Stokes numbers, the capture efficiency is actually very low as well. As the Stokes number increases, it undergoes a sharp transition to a high capture efficiency right around this critical Stokes number range where inertial effects come into play. Now again, going back to this figure, it's easy to understand why. When you have small Stokes numbers, basically what it means is particles are following fluid flow. So the probability of them getting captured on the surface is low. When the Stokes numbers are high, many of these particles are detaching themselves from the flow streamlines and directly approaching the surface, and therefore the probability that they will stick to the surface is high. That is why we see this effect of Stokes number on capture efficiency, where as the Stokes number increases to 0.1 and beyond, there is a sharp spike in the capture efficiency. So here again, if you're trying to minimize this, your approach should be to minimize this, right? If you keep the Stokes number for the problem low, then in principle your capture efficiency should be reduced as well. How do you reduce Stokes number? Going back to the equation we had written earlier, you either reduce S or you increase D, right? But I mean, is that a good strategy? What does it mean when you increase D? If you increase the characteristic dimension of your surface, the capture efficiency may be lower, but the total surface that's available for capturing particles will be much higher. So that's not a smart strategy. How about lowering the numerator, the stopping distance? Is that a good strategy? Well, it is if you are only again concerned about minimizing inertial capture. Remember that this is characteristic of inertial capture of particles. If you try to lower your Stokes number by reducing the size of the particles, yes, you will be reducing inertial deposition, but what's going to start happening? Diffusional deposition is going to increase, electrostatic deposition is going to increase, and even phoretic phenomenon, which we'll talk about later, start to increase. So coming back to the sketch, when particles are very fine, I said that they follow streamlines, but that's not strictly true, right? When do particles deviate from flow streamlines? It happens in both extremes. When the particles are very large, they deviate from flow streamlines because of inertial effects. But when particles are small, they also deviate from flow streamlines because of diffusional effects. So for example, you want to minimize collection of particles on the surface, so you eliminate all supermicron sized particles and substitute them with nano-sized particles. Is that good? Well, what's that's going to happen is all these nanoparticles are going to have very high diffusion rates, and so they are going to start again depositing on the surface by diffusional means. Or if there is a thermal gradient, again the finer the particle, the greater will be the effect of what's known as thermal diffusion or thermophoresis. That will also aid in the collection of particles. So it's not a clear-cut solution to say that if you do size reduction, it might seem like a simple strategy. If you can reduce the size of the ash particles, for example, that survive the combustion process, that should result in less fouling. But that may be too simplistic a viewpoint, because as you reduce size, yes, you are reducing inertial collection, but you may be increasing diffusional and phoretic collection. Although I will say that based on practical experience, it still pays to do size reduction, because inertial effects are order of magnitude greater in their influence compared to diffusional and phoretic effects. So it's an interesting optimization problem again. If you look at overall collection efficiency, not your inertial capture efficiency, but supposing I were to plot eta collection versus dP, where I'm including all possible mechanisms of particle collection, then will I see a trend that looks like this? Not really. Instead, what you will see is a trend that kind of looks like this, where again going from 0 to 1, when the particles are very, very fine, let's say that this is 1 nanometer, the diffusional deposition actually causes an enhancement in collection efficiency. And then as you keep increasing the size, let's say that this is 10 nanometers, 100 nanometers and so on, you actually get a reduction in overall collection efficiency for a size that is slightly below 0.1 microns, because inertial effects have not set in yet, because as we have seen before, inertial effects start to become important when you start exceeding Stokes number. Sorry, this should be if you write this in terms of the particle diameter, that's probably not a good measure. Let's go back to our Stokes number representation. So here again the Stokes number here is 0.001, 0.1, 1, 10 and so on. The minimum occurs below 0.1 microns, and then as you start crossing 0.1 in Stokes number, you start to see an increase in your collection efficiency. So when you plot collection efficiency as a function of Stokes number, including all collection mechanisms, then there is actually a fairly high collection efficiency at very, very fine sizes, which drops rapidly to its minimum value somewhere in the 0.05 Stokes number range, and then as the Stokes number starts to approach 0.1 and exceed 0.1, again the numbers pick up. Again, the primary reason is here you are dominated by diffusional phenomena, and in this part of the curve you are dominated by inertial phenomena. So that is why the Stokes number is a very critical parameter to characterize the particle transport and particle deposition mechanisms that are prevailing in a system. But at the same time, if you entirely focus on inertial effects and forget about the diffusional effects, you could be making some miscalculations in your analysis. So from this you can see that it is true that in the inertially dominated regime, your collection efficiency will be significantly higher compared to diffusionally dominated regime, but this non-monotonic behavior is very important to characterize and understand. So you should be able to essentially sketch two behaviors. If you want to look at the effect of Stokes number on capture efficiency in the strictly due to inertial mechanisms, then this is a curve that applies. If you want to look at the effect of Stokes number on the overall collection efficiency, including all transport mechanisms, that is inertial, phoretic, diffusional, then this is a kind of qualitative relationship that you will find. Okay, so you have to be able to distinguish between the two. Okay, so what we have looked at so far is the effect of particle transport and the associated collection efficiencies on surfaces. Now, as chemical engineers, we always like to non-dimensionalize, right? So when we look at these particle collection rates on surfaces and particle diffusion fluxes, we would also like to define certain reference values which we can use to convert these fluxes into their dimensionless values. So what are the relevant non-dimensional parameters in this case? In order to define the reference values, you have to look at two cases. One is the quiescent case, and the other is convective. Now, when we talk about quiescence versus convection, what we are talking about is here there is essentially an absence of a convective velocity, either forced or natural convection, whereas in this case there is a significant convective component, which again can be forced convective or natural convective. Now, in the two cases, how do you define reference fluxes? So if you take MP dot double prime reference, where again M stands for mass, P stands for particles, dot stands for per unit time, and the double prime stands for per unit area. So what this is particle mass flux reference. In the case of quiescent flow, it relates back to the diffusive characteristics of the particle. so this will be an MP dot double prime reference diffusive, because diffusion becomes the only prevailing transport mechanism if you have a completely quiescent system. Whereas in the case of convective, your M dot double prime P reference is a convective parameter, taking into consideration the fact that convection does play a major role. So what's the difference between these two? You have to go back to your expression for diffusive flux. If you recall, the expression for MP dot double prime diffusion equals minus dP rho gradient in omega p, right? The diffusional flux of particles is proportional to its mass fraction gradient, and it's related by the Brownian diffusivity dP and the gas density or fluid density rho. So if from this, what would you establish as a reference flux? This is the reference flux, therefore is going to be dP times rho times omega p at the surface minus omega p far away from the surface, the whole thing divided by L. So the term within the parenthesis is a reference value for the gradient. And for this case, for the convective case, actually the reference value is much easier to think about. It's basically rho times U, which is the convective flux of the fluid multiplied by omega p W minus omega p infinity. So when we actually take the prevailing mass fluxes and we want to non-dimensionalize them, we will divide by this value in the case of quiescent flow, and we will divide by this value in the case of convective flow, and the resulting non-dimensional parameters that you obtain are what? In the case of quiescent flow, what is the non-dimensional parameter that represents mass flux? Nusselt number. So here you will define a Nusselt number for mass transfer for a particle, and in the case of convective, you will define a Stanton number for mass transfer of the particle. The Nusselt number and Stanton number are critical non-dimensional parameters that govern transport properties and fluxes of particles in systems. So we'll come back to this in the next lecture and discuss in more detail. It turns out that the Nusselt number is a function of primarily the Reynolds number and the Schmidt number of the particle. The Stanton number is also a function of the same two parameters, because the relative dependence is going to be very different in the two cases. In the case of the quiescent flow, the Reynolds number effect, which is the convective effect, is going to be significantly lower compared to the diffusive effect that is represented by the Schmidt number, whereas in the case of convective flow, the Reynolds number effect is going to be significantly greater than the diffusional effect that is represented by the Schmidt number. So we'll come back to this and go through the definitions of these numbers, and it turns out that you can actually relate these parameters back to your capture efficiency. So we'll do that in the next lecture. Okay, any questions? All right, see you at the next lecture then.